So, yeah. Okay, so hi, can you all hear me well?
Yes.
Good. I also send you the Jamboard link if you want to open the Jamboard on yourself. Let me send it again because probably there are. Okay. Here it is. So let's start. Let me remind you what we did last time. So we started our discussion about operator systems. I remind you that we fix a unital sister algebra A, and then any subspace S in A is called an operator system if it contains the identity element of the sister algebra, and if it is self-adjoint. Self-adjoint here means that, I mean, this S star is just all the X stars X in S. So I just take all the stars of the elements, and I need my subspace to be closed under the star operation. And the first example of an operator system was any sister algebra, of course, is an operator system. But in fact, okay, maybe before that, in fact, whenever we have a sister algebra A, then there is another sister algebra, M and A, that is just n by n matrices over A. And therefore also M and S will be an operator system. And whenever I have a map phi from an operator system S to an operator system T, then I also have a map phi n from the operator system Mn of S to Mn of T. And if the original one was linear, then this will be linear. And if the original one was bounded, this will be bounded, of course. Okay? Now, but one thing you have to keep in mind is that, well, while right, how did we define the norm on M and A? The norm on M and A, we thought of putting A in some B of H, and then we could put M and A inside B of H to the N. And eventually we said that the norm coming from this embedding does not depend on the choice of the original representation, because of the property of sister algebras having unique norm. Same goes for positive elements. In operator systems, this is not the situation. I mean, these guys, they depend on the original embedding of S inside the sister algebra A. So I can embed S in another A, in some B, and then to get things that behave differently. But we will discuss this later, don't worry. But this is just something I wanted you to have in mind in the meantime. And now some quick definitions. So phi is called positive. So these are definitions also from last time. Phi is called positive if it maps positive elements to positive elements. And it is called n positive if phi n is positive and completely positive if phi n is positive for every n. Same we have n contractive and completely contractive. And then we have completely bounded. So a map is completely bounded if phi is bounded, then all the phi n's are bounded, and the supremum over all the norms of phi n is finite. Okay. And the way the motivation I gave you last time for the definition of operator systems, you know that they carry an extra baggage of structure of positive elements and norms on these guys, on the Mn of S. So in some sense, completely positive maps, and okay, and we also have the unit. Okay, so let me just mention that if you have a unit, if phi is unital, then this is called UCP, this is called UCC, and this is called UCB. So in some sense, the morphisms that will remember the structure we have will be UCPs plus UCCs, right? UCP and UCC are the right morphism that remembers all the structures of all this extra baggage of norms and the positive elements. So our goal should be to understand UCP and UCCs, okay? But we will start just for positive maps. But before that, let me give you an example. So example. If A and B are sister algebras, then pi from A to B is or you know what? Let me do it like this. Let me say if A is a sister algebra, is sister algebra, and phi from A to B of H is a star representation, then well, I claim that pi is positive, right? Why? Because then pi is positive because pi of A star A is pi of A star pi of A, right? Plus contractive, plus pi n that goes from Mn A to Mn of B of H, which is also B of H to the n, is also a star representation. So it is also positive and also contractive. So pi is Cp plus Cc, completely positive and completely contractive. And if it was unital, then it is unital completely positive and unital completely contractive. Okay. Second example. So I'm going to do something to the first example. If to compress it, if V from so let's assume now, okay, maybe in the last example, okay, maybe let me add here just one comment. If pi were unital in the previous example, then pi is UCP plus UCC כמובן, טוב לא אמרתי כלום, זה רק טרמינולוגיה, אבל עכשיו, but now, let V from K to H be an isometry. Okay, so V star V is the identity of H. And let pi be, as before, So it is unital star representation. And consider the following map. So let phi will go from A to B of K, and it will be phi of A will be V star of pi of A V. So now that phi is unital, right? So phi is unital. It is positive. Why? Because, well, I mean, okay, there are many ways to think about it, but the easiest to, okay, I'm moving to the second page, but you probably know that T, probably we used it before. T in B of H is positive if and only if for every sine H, T psi, or psi T psi is positive. So if A is positive, then for every psi in K, psi phi psi, which is psi v star pi A v psi is v psi pi A v psi, right? And if A is positive, then pi A is positive. So you apply it on the vector v psi, so you get something, right? So phi is positive and clearly contractive too. But now, what is phi n? Phi n goes from right mn of A to B of H K to the n. And it looks like this, right? Phi n of Aij is V star pi Aij V, which is like many V's star pi Aij, many V's without star. So it is nothing but V to the n star pi of Aij pi n, V to the n. So you see that I mean, and so now this is an isometry, right? This is a representation. So it is another kind of phi. So phi n is another kind of phi. So if I said before that phi is positive and contractive, then phi n is also positive and contractive. I mean, they're of the same form. So from the same reasoning that we had before, phi n is positive and contractive. And this was true for any n, right? So phi is UCP plus UCC. Okay, so we took I'm going to the previous page just to give another explanation. We took a representation pi. We took an isometry of another Hilbert space K into H. So you know, if you think about, you can think about, let me maybe write this here in red, can think about Vk as sitting inside H, right? So in this sense, if you think about K sitting inside H, then phi A is nothing but the projection onto K. I mean, this is isomorphic to K. So it is the projection onto K times phi A restricted to K. So in other meanings, pi is a dilation of phi, right? We defined the dilations of maps last time. So pi is a dilation of phi. So we just showed that dilations of compressions of compression is the opposite of dilation. Compressions of star representations are UCP and UCCs, and we will show next time or next time that these are the only examples in some sense. So later on, you'll see this is in some sense the only example. Just like the only example of a state was in fact a vector state. This was the GNS, right? The GNS told us that any state is a compression to one-dimensional space of a star representation. So this was our first example, and then we said that from the GNS it is the only example. So same goes here. But before that, there are lots of things we will probably want to do. And let me start just by giving you a counter example. By the way, if you have questions, feel free to interrupt it. I mean, always. Because, okay, we're not in class. I can't see your, well, I can see some of your faces, but not all of you. So feel free to stop me.
Guy?
Yeah, hang on.
So you say that it's the only example for UCP maps, right? That's what you're saying?
I said it's the only example
of
okay.
what?
I said UCP plus UCC.
Yeah, so I mean, we should assume one implies the other somehow, no? Or
I didn't.
Like only example of what?
We're going in this direction, of course. So Alon. So right now I just said this is the only example. This is okay. Right now I said that the maps we're looking for are UCPs plus UCCs. These are the correct maps. The correct morphisms in our category of operator systems is maps that are UCP and UCCs. And yes, I know I said U twice. I mean, probably I should have called them UCPC or something like this, right? Or UCCPC, I don't know. But later on, I mean today, I hope, we will see that it is enough to assume that it is only UCP or only UCC, and it will imply the other property too. But before going in this direction, let's stay at least in the next hour in the notion of positivity and discuss about just positivity, being positive, or I want to understand connections between positivity and contractivity and vice versa, and between positivity and complete positivity. Are there maps that are positive and not completely positive? I mean, maybe every positive map is completely positive, etc. So let's start thinking about these things before moving on. So let me give you right away a counter example. I mean, it is a classical counter example of a map that is positive but not completely positive. And this is an example you should keep in mind. So counter example. So example for positive but not completely positive. Well, I'm going to give you one example, but then I will say that I'm going to give you a bunch of examples that will be similar to this one. And then let me start with this one first. So let phi from M2 to M2. M2 is M2 of C, okay? Whenever I write Mn, I mean Mn of C. And from M2 to M2 be the transpose map. So phi of A is nothing but A transpose. So clearly it is positive, right? So if A is positive, then A transpose is positive. Right? You can think about what does it mean to be positive? It means to be self-adjoint. And the spectrum, in this case, the eigenvalues, positive. The same will go with the transpose, right? But so phi is positive, phi is positive. Okay, I said that it is going to be an example for positive, but not completely positive, but it's also going to be an example of contractive and not completely contractive. So let me also mention that it is positive and phi norm is 1, of course. But but we have phi 2. Phi 2 goes from M2 of M2 to M2 of M2. Each of them is like M4, right? So what is phi 2? So let A now be the matrix E11, E12, E21, E22. So EIJ is the matrix that is 0 everywhere, and as 1 in the IJ entry, right? So this is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay. So let's think about this matrix. What do you know about it? What are its eigenvalues? Well, it has, of course, the 0 eigenvalues because it's of rank 1. Do you see it? So it has the 0 eigenvalue appearing 3 times. And then the eigenvector 1, 0, 0, 1. I mean, this is an eigenvector that corresponds to the eigenvalue 2. So the spectrum of A is nothing but 0 and 2, right? So spectrum of A is 0 and 2. Right? But what about A transpose? But phi 2 of A, it's not A transpose, it's phi 2 of A, which is putting transpose on each of these guys. Right, this is, well, you see, it's a permutation matrix. In particular, it's unitary, right? And it's a self-adjoint, so its spectrum has to be, well, it has to be in -1, 1. Right, because it's unitary, but real unitary. So what? So we see 2 things. One, phi 2 is not positive. But also, right, if you do phi 2 twice, then you get identity, right? So if you call this matrix B, then B is of norm 1, but phi 2 of B is of norm 2, right? because phi 2 of B is A. So, so phi 2 is also not contractive. Okay, we only show that it is greater than 52. Sorry. Right? So this is an example of a map that is positive, but not completely positive, or not even too positive, contractive, and not too contractive. In particular, not completely contractive. And it is, of course, unitary. So, okay.
And
So,
Guy?
yes?
At some point at one class, you gave us the example of the function x squared as a function which is monotone, but not, I don't know, completely monotone or something like that. I wonder if you use this also to get a positive, but not completely positive map, like the function from C to C, which is x goes to x squared. Or
it is not linear. It is not linear. I mean, we consider only linear.
We need linear. Yeah, part of.
Part of the structure of the theory is.
Okay, when you say positive, it's in particular linear.
Yes, I mean, I gave the definition in the first. Yes, well, I only consider linear maps. I mean, that's the. We're dealing with subspace.
Okay.
Yes. Positivity in CX would automatically pass to complete positivity. So.
Yes, but we don't know it yet. But you're right. Okay. So okay. So this is an example I want you to have in mind, and I also want you to think more about this example. So what happens if what happens if I do it for? Okay. So what happens? What happens with a transpose map phi? So we not phi, psi from M3 to M3. Phi of A is equal to A transpose. Of course, it's not going to be. It's going to be another counterexample, but what will be the counterexample? I mean. I mean, of course, it's not going to be 3 positive and 3 contractive, but will it be 2 positive and 2 contractive? No. So if you check it and do the computation, you will see that in fact psi 2 is not positive and not contractive, and in fact the norm of psi 2 will be greater than or equal to 2. So you can do something better than that. You can take like the transpose function on infinite by infinite matrices. So what happens? Okay, I will leave it to you to think about it. With, I don't know, rho from B of L2 of n into B of L2 of n, and transpose function. So you know how to define it. Just think of B of L2 of n as an infinite by infinite matrices and define the transpose. It will be bounded, it will be positive. But you will see that the norm of rho n will be greater than n. So this means that rho will not even be UCB. Right? We had this notion of completely bounded. This rho is not going to be even completely bounded. Not only, I mean, it's not going to be completely contractive, but even more than that. So rho is not completely bounded. Okay. I mean, you can imagine this. I mean, it's not hard to show it. I mean, but I leave you this as an exercise. Okay, I move to the next page. Sorry. And let's begin the discussion I wanted to have about positivity and contractivity that I said before. So let's start maybe with a quick claim that I just want to write it down, but we know it. Positivity, I mean, if phi is positive, it implies that phi is self-adjoint. Okay, and you know how to prove it. We did this a couple of times, right? Exercise. Verify that you know how to do it. I mean, this is something we did a few times already. You decompose A as B plus IC, and okay, do it. Exercise. Okay, now claim that I will prove with you. Let phi from S to T be positive. Then phi is bounded, but something can go wrong. It might be that it is not well, I mean, that it is not contractive, that the norm of phi is less than or equal to 2 times the norm of phi1. By the way, do you see it? I mean, some of you see it also in the Jamboard. It looks okay? Yes. Well, I answered to myself because I also opened it in the Jamboard in this computer. So, okay. You see it works fine. Poof. Okay, so in fact, this factor 2 is going to come into picture only when we will consider elements that are not self-adjoints. But in fact, for positive elements and for self-adjoint elements, we will not need these two. These two will only come at the end. But it will be there. I mean, we will not be able to get rid of it. We will want to get rid of it, but we won't be able always. So let's see what happens. So if x is greater than 0, then clearly x is less than the norm of x, right? And therefore phi of x is less than x times phi of 1. And therefore phi of x is its norm is less than phi of 1 times x. Now, you know, if x1 and x2 are positive, then obviously x1 minus x2 has to be less than the norm of x1 and greater than minus the norm of x2. right, this is because right, because this inequality is nothing but to say x1 is greater than minus norm of x2 minus x2, which is obvious because x1 is positive, and in the left-hand side there's something that is negative. And similarly, we have similar inequality here, right? So x1 minus x2 norm is less than or equal to the maximum when we understand its spectrum, right? So we know it's norm. Is this okay? What I just wrote? Okay. I mean, if you need further explanation, let me know. But just note that we have this because this is going to be the whole idea. So now, if X is self-adjoint, then we can decompose it and we can write it as a sum of two, as a difference of two positive elements, and plug phi into the story. And we get from what I wrote above that phi of x norm is less than or equal to half times the maximum of the norm of phi of norm of x plus x, phi of the norm of x minus x, which will be less than or equal to half of the norms of x plus minus x times phi of 1, which is less than or equal to x times phi of 1. Right, so for self-adjoint elements, we have what we want without the 1. Without the 1. Now, the problem is for elements that are not self-adjoint, and here we'll get the 2. For a general X, write X as A plus IB, AB self-adjoint, then norm of A and norm of B, of course, less than the norm of X. Then phi of X will be less than 2 times X times phi of 1. Because you do it to A, to B, and so I forgot the norm here, and I think that's it. Okay? Yes, Itamar? I thought you wanted to say something. Okay. So let me show you an example that this is indeed the worst case scenario. And no, that shows not that this is the worst case scenario, that shows that the worst case scenario can happen. I mean, that we can get these two. And this example is due to Arveson. And this example will have another importance later, so keep it in mind. So I already showed, I mean, we discussed about the example of this function system. So we take S to be the span of 1, Z, Z bar. You think of it as sitting inside the continuous functions over the circle. And how does the general element in S look like? Well, it looks like A plus BZ plus CZ bar, right? This is a general element. and it will be positive if what? Well, it will be self-adjoint. I mean, this is positive if and only if, well, it will be self-adjoint if A is in R and C is equal to B bar, right? This will make it self-adjoint. And to be positive, you will also need that, put it in the other, I mean, well, it's an easy computation. You'll get A greater than to the absolute value of B. So this will make it self-adjoint. This will make this positive. I mean, this is an easy computation. Now let phi from S to M2 be defined like this. Phi of A plus BZ plus CZ bar is going to be A, 2B, 2C, A. This is, of course, linear, and it is also positive, right? Because for a 2 by 2 matrix to be positive, you need the diagonal elements to be positive and the determinant to be positive. And it will be positive exactly when A plus BZ plus ZZ bar will be positive. So, this is positive. However, well, phi of Z has norm 1. So, right, because we are on the circle. So phi of Z will be less than the norm of phi. On the other hand, phi of Z by definition is nothing but 0, 2, 0, 0, which has, of course, norm 2, which is also equal to 2, 5, 1, if you want. Okay, so in this example, the norm of phi is 2 times the norm of phi 1. I mean, it's less than, but we know that this is the worst case scenario because of the previous theorem, so it has to be equal. Okay? Okay, now, let me give you an exercise. I think this was one of the exercises that Alon mentioned before. If T is a function system, well, not exactly, it's not what he mentioned before, but similar in fact. That is to say that T sits inside a sister algebra like this, C of X. Then any positive phi from S to T has a norm which is equal to phi 1. Let me even give you the answer. I mean, what's the easiest way to do it? First, think of the case that T is nothing but the complex numbers. If T is nothing but the complex numbers, then phi is just a positive linear functional. But okay, but now there are things we know about these guys, and you can use them, and then using evaluation at points, you'll be able to generalize this to any commutative. I mean to the case that T is equal, let's say, to C of X, which is enough. Okay, so anyway, think about it. Okay, But now, so of course, when we have a positive function, okay, so maybe let me write this. I'm moving to the fourth page. So remark we saw that if phi is positive and phi of 1 is 1, then what can happen? The normal phi will be between 1 and 2. Right? I mean, these are the options. Now let me tell you what can go wrong. So two factors can make phi to be strictly greater than 1. One, this is what we saw, non-commutativity of the range. And let's say this you see from the previous example plus previous exercise. Right? The previous example tells us that we had a range that was M2. Although the domain was commutative, the range was non-commutative, and we got norm that is 2. The norm of phi was 2, although it was a positive map. And the previous exercise tells you that if the range is commutative, even if the domain is not commutative, this can't be the case. The norm will be 1. So non-commutativity of the range can ruin this. Second thing that can ruin this, that can make the normal phi be greater than 1, is the lack of sufficiently, probably I write this incorrectly, many positive elements in the domain. What do I mean by this? I mean that the domain is a function system. In some sense, the best function systems, the function systems that has many, I mean as many as they can, positive elements are sister algebras. So if you take function systems in the domain that are sister algebras, or in some sense close to be sister algebras, then you will get that the norm of phi is 1. I'm not going to show this because at the end we're not going to be, we're not going to care a lot about positive functions. We're going to be interesting in UCPs. But what, Alon?
You mean operator systems, which are sister algebras, right?
Yes.
You just said function systems a few times.
Sorry, I meant operator systems. Yes.
Right. Thank you.
So maybe let me write this. Let me write. We can show, and maybe I will give it as an exercise. I don't know yet. I need to think about it if it's interesting enough. We can show that if S is a sister algebra and phi from S to T is positive, then the norm of phi is phi of 1. This is in fact a theorem of due to Russo and Guy. So now that I told you the name of the theorem, I can't give it as an exercise, right? No, I'm joking. Okay, so again, why I feel fine with not doing this, because at the end, eventually we're going to care about UCPs and UCCs, and then we're going to figure everything out. But right now, I mean, this is interesting. Okay, what about the other direction? So right now we discussed about if we know that the map is positive, do we know that it is contractive, or what can go wrong? And we said that, well, what can go wrong is that the norm can be between 1 to 2. This is the worst case scenario, is that it will be 2, but it will not happen unless there aren't sufficiently many elements in the domain, or the range will be non-commutative. I mean, and I don't know, I said it.
So we should understand this remark. When you say 2 factors, you mean that you need 2 of those, like you need
one of them can ruin the norm.
But not alone one of them. You need both of them in a sense. No, I thought because okay.
No, the previous example. You say, well, of course, both of them. I mean, if the domain is a sister algebra, then it doesn't matter what the range is. Yes.
Yeah.
Or if the range is a function system, it's commutative, then it doesn't matter what is the function, what is the operator system in the domain. Yes. The other direction, going from contractivity to positivity, is much easier. So let's do it. So what about going from contractivity to positivity? Well, here we don't have problems. We always have this claim. Phi from S to T, S is sitting inside A, say, is unital contraction implies that phi is positive. In particular, what? In particular, UCPs are UCCs, right? In particular, UCCs are UCPs. What else? In particular, well, states, or yes, we didn't define yet states, but okay, never mind. Okay, so proof. Right, when we discuss about map, we can always assume that the range is everything. I mean, we don't need to care too much about the range, right? If we want to prove positivity, say, or contractivity. So we can assume without the loss of generality that T is equal to B of H. Fix a unit vector. Then f of x, which is psi times phi of x psi, is what? Well, we know that phi is unital and contractive. So this is unital and contractive, right? It is unital and contractive. Right, but f is in S star. It's a linear functional. What does the Hahn-Banach theorem tells us? That we can extend this to a linear functional over A, right? Over the sister algebra. Bayan Banach, קיים F twiddle in A star. F twiddle also has norm 1. It will also be unital because it's an extension, right? Such that F twiddle restricted to S is F. But this tells us that phi twiddle has to be a state. And we know that states are positive from our discussion about states of sister algebras. So phi twiddle is a state. Right? You remember in sister algebras, to be a state, you only need to have 2 properties out of 3. So in particular, it is positive. So phi is positive, so F is positive. But this exactly means, by definition, or by not by definition, but by positivity in Hilbert spaces, that phi x is positive. So phi is positive. So this was immediate only because all the hard work was done here. I mean, this is not an easy claim. This claim is not easy claim. All the hard work was done here. We already did this when we discussed about states in sister algebras. Okay? When we proved the theorem that tells us that 2 properties of being states are enough to imply the 3rd one. So if you're unital and contractive, then you're positive. Okay. So what? So can we do better than this in the sense of the type of the domain? What do I mean by that? A question, can we do better than this in the sense of the domain, of the type of the domain? What do I mean? The domain here was an operator system, but the assumption on phi was being unital contractive. This has nothing to do with the structure of operator system. Well, positivity, yes. The implication has to do with the structure of being operator system. But the if part, the assumptions, has nothing to do with the structure of operator systems, right? I could tell them just about a unital subspace of a sister algebra. And this is in fact quite important. So I do want to emphasize this. So claim, let M be a subspace of a unital sister algebra. A containing 1. So these are also called operator spaces. Okay. Let S be M plus M star. So M is operator system, of course. If phi from M to T is another operator system. T another operator system is a unital contraction, then the map phi twiddle that goes from S to T and is defined by A plus B star goes to phi of A plus phi of B star. for every A in A and B in B, A and B in M, where will I write this? Let me, can I do this? Can I? Never mind. Okay. So for every A and B in M is well defined and is the unique extension and is the unique extension of phi into a positive, or yes, into a positive map on S. Okay, is the claim clear? So the claim tells us that if we start with a unital contraction on an operator space, namely on a unital subspace of a C-star algebra, then we can extend it to a positive map on the operator system in a unique way. In some sense, this should also tell you that if you understand the category of operator systems with UCPs, then you understand also the category of operator spaces with unital contractions, with unital completely contractions. So maybe let me say a remark. Okay, okay, I will not write this, but you understand. So proof.
Wait, so you do not guarantee that the extension is also contractive, right? And there's no reason actually.
No, there is no reason. But in the completely version, of course, it will be contractive too. It will be completely contractive. Oh, we didn't see this yet, but
yes, okay.
Okay.
Thank you.
You're welcome. Yes, right now we're zooming into positivity and contractivity. At the end, we will use these results in the completely way. So, okay, so uniqueness is clear, of course. Uniqueness is clear. Why? Because we know that if phi is positive, then it is if phi twiddle is positive, then it is self-adjoint. Then it has to be of this form. I mean, if it works, it has to look like this, right? Because once phi twiddle exists and positive, then it is self-adjoint. So then I mean it has to look like this. It has to map A plus B star to phi twiddle of A plus phi twiddle of B star, which could be phi of A. Well, you understand. So okay, so uniqueness is clear. What about showing it is well defined? To show, so this was uniqueness. To show phi twiddle is well defined. What do I mean by well defined? I said before that what's the definition of phi twiddle? The definition of phi twiddle was that A plus B star is going to be phi of A plus phi of B star. But what happens if A plus B star is equal to C plus D star? Right, so if A plus B star is equal to C plus D star, then A minus C is equal to B minus D star, right? So but this is, so A minus C will be both in M and in M star, because B minus D is in M. And I want to show, I want to know that phi of A plus phi of B star is equal to phi of C plus phi of D star, meaning phi of A minus C is equal to phi of B minus D star, right? This is what I want to show. So what do I really want to show? I really want to show that phi is self-adjoint on M intersection M star. So we need to show, phi is self-adjoint on M intersection M star, and the only place it can be self-adjoint. But what do we know about this intersection? This intersection is an operator system. It is self-adjoint and unital. Is operator system. And phi restricted to this is a unital contraction. Hence positive. Hence self-adjoint. So phi twiddle is well defined. Now it remains to show that phi twiddle is positive. It remains to show phi twiddle is positive. And without the loss of generality, again, we can assume that T is B of H, fix psi in H. We want to show that psi of times phi of A twiddle psi is greater than 0 for every A greater than 0. Let rho of A be a psi phi of A twiddle psi. Rho, let me call it F, okay. Then F, F as norm. Well, yes, I want to say that it has norm 1, so I need psi to be a unit vector. So I go up and say the fixed psi a unit vector. Okay, so phi is norm 1 by Han-Banach. Well, same trick as before. F extends to contraction, a unital contraction F twiddle on S, which is equal to M plus M star. And therefore, from what we said before, phi twiddle is positive. But F twiddle of A plus B star is F twiddle of A plus F twiddle of B star, which is F of A plus F of B star, which is psi of phi twiddle of A plus B star of psi. So the extension has to be the extension in some sense. I mean, right, we extended something small and it coincides with what it has to be in some sense. Thus, we're done. Thus, if A is greater than 0, phi twiddle of A is greater than 0. So psi, phi twiddle of A, psi is greater than 0. Questions? Okay, if not, let's do one last thing and then we take a break. Well, maybe before that, an easy exercise. Easy exercise. If phi from S to T is positive, then its unique extension, right? I can always extend it to a linear continuous map. I mean, to a continuous map, which will be linear, of course, to the closures. I remind you that I never assume that the operator systems are closed, but this will be positive too. Okay, that's the norm closure in the system algebra. Okay, and now let me give you a corollary, and then we'll take the break. So I move to page 6. Corollary from what we did. Let T be a contraction on a Hilbert space. So when I write T in BH1, I mean in the unit ball, in the closed unit ball of B of H. Okay, its norm is less than or equal to 1. Then I claim that there exists a map, let's call it rho T, from continuous functions over the circle. It will be a UCP onto B of H, not onto, into B of H, such that for every two polynomials, P, Q, in complex polynomials in complex variables, rho T of P plus Q bar will be equal to P of T plus Q of T star. Before proving this, let's read this again. I mean, this is quite an amazing corollary. It tells us something. Okay, let us recall for a second, what do we know about, let's say, normal elements, right? A normal element in B of H, then we know, okay, not normal, I want the spectrum to be in the continuous, in the circle. So unitary element. What do we know about the unitary element? Unitary element, its spectrum is inside the circle. So I can always take a continuous function on the circle and evaluate the function in a reasonable way with the unitary, right? This was the continuous functional calculus. So on polynomials, it will give you what you would imagine, but you can generalize this to any continuous function. So I claim that you can do the same thing, not with unitary, but with contractions, but you won't get a star homomorphism. So with unitary, it was with star homomorphism. It was the continuous functional calculus was in the sense of sister algebra, so it was up to star homomorphism. Here it will be up to UCP.
And only polynomials.
What do you, I mean, you'll be able to evaluate any continuous function. This is what I claim. It will be reasonable on polynomials. On polynomials, you will get what you expected to get. That's the same story that you get somehow on unitaries, right? I don't know what is an exponent of unitary. I don't know, but on polynomials, I know what it should be, and then I know it behaves in a reasonable way. When we discuss about unitaries, we got a star homomorphism. Here we get only a UCP, which is the best second thing.
But why you don't get it on the, you don't get all continuous function on the unit disk, only on the circle, no?
So,
I mean, you
yes.
See what is bothering me?
Yes, I see what is bothering you, and I know what's bothering you. I mean, the thing is, it's more tricky, yes. So it's somehow you need to choose between two worlds. The world of holomorphic functions, let's say the disk algebra, that you can embed into continuous functions over the circle, or the worlds of, I don't know, operator systems generated by polynomials in a Z and Z bar somehow. And the thing is that, well,
You say it's more of a, like an extent, like it comes from the fact that when you have Z and Z bar and you talk about algebras, you get all the continuous functions on the disk, but when you only talk about subspaces, then you get continuous functions on the circle, right?
No. The thing is that somehow we need something that would, there is a more general result. Maybe I will discuss it, maybe not later on. But to have such a property, you need the spectrum of your operator to be in a set, and to consider the boundary, the topological boundary of the set. And the reason for that is that some notions should live together in a pleasant way somehow. When it's unitary, you don't see it somehow. So, I understand your question, and yes, I don't understand how to completely answer your question appropriately, but maybe we'll discuss about these issues later. Okay. Okay, but right now let me just quickly prove this corollary and take a break. So proof. I mean, it's going to follow immediately somehow from the von Neumann inequality that we mentioned last time. So consider, and from the claim we just proved, consider this, the polynomials as a subspace of CT, continuous functions over the circle. Let rho t from C of Z to B of H be defined by taking P into P of T by the von Neumann inequality, by the von Neumann inequality. So the von Neumann inequality, we proved it last time. It tells us that P of T norm is less than the supremum of P of Z, Z equal to 1. Okay. So by the von Neumann inequality, we know that rho t is unital contraction. Is unital contractive. So by the previous claim, the map rho t it will, which I denote it by rho t again because that's the notation of the claim, that maps P plus Q bar onto PT plus QT star is positive. Well, is well defined and positive, is well defined. Positive. And this extends by the exercise. By the exercise, well, plus Stone-Weierstrass. Plus Stone-Weierstrass to continuous functions over the circle. So, but why is it completely positive? I discussed only about positive things, right? Yes, okay, this was too early. Okay, so let me change the corollary to positive here. That's the corollary. Positive. And remark, we will see that positive maps on commutative sister algebras are completely positive. Okay, maybe today even. So, but okay, so let's take a break of 15 minutes. טוב, חבר'ה, חוזרים? נחכה חצי דקה, אבל אם אתם יכולים לפחות תשמיעו קול שנראה שחזרתם. אז אלון פה, אורי פה. אפילו בצ'אט, מי שחזר ואין לו מצלמה או אין לו מיקרופון. איתמר, חנה, are you here? יונתן?
I'm here.
מיכאל? Who is in the library, by the way? I see that there is somebody. Okay, so regarding the last corollary, I want to mention another thing. So, historically speaking, this map, the positivity of this map was already important to people like Feyer and all these people you know from Fourier analysis. And in fact, they proved that this map is positive. In fact, that it is positive on polynomials in Z and Z bar by hands. And think about it. I mean, you can try to do it, but it is quite a tricky exercise to prove by hand the positivity of Roti. I mean, to show that positive, to figure out what are positive polynomials in Z and Z bar, and to show that this map maps them to positive operators. I mean, it's possible to do it, but it's long and tricky. So another remark, I think it was Feyer, I don't know how to call it, Feyer and others, I don't know, showed and were interested in this Roti, that Roti at least may be restricted to polynomials in Z and Z bar is positive by, is it reasonable to call it by hands? I don't know. I mean, they checked what is the correct, how does polynomials, positive polynomials look like, and this is let me say non-trivial work. But you are able to do it, I mean, but it will take you a lot of time without okay, so what are the tools that we used? We used somehow logical things. We didn't לכלכנו את הידיים שלנו איכשהו. Okay, which is cool, I think. Okay, so now we move to completely positive maps. So we discussed about positive maps, and now completely positive maps. Let me start with it.
Guy, do you have it's probably very silly, but do you have an example of a positive polynomial? Like a polynomial which is positive on the circle?
Z is not positive, it is not even self-adjoint. So first the polynomial be self-adjoint, like Z plus Z bar.
But here in the corollary, you're not allowing such things.
What do you mean by that?
when you stated the corollary, you're looking at polynomials, like strictly polynomials only in Z, not in Z bar.
No, in Z bar.
Ah, but you didn't write it in the corollary.
Because I write Q and Q bar in the, I mean, I wrote
it. Yes, okay. Yeah. Okay.
But it's the same thing.
Yeah, of course. Yeah, okay.
Okay. Okay. So, right, because when I think of them as the functions, they need to be positive numbers. I mean, the values of the functions needs to be positive numbers. There isn't a special meaning here. Right? These are just positive functions. Every number on the circle, it is positive. So first it needs to be real. So it has to be polynomial such that the Z bars and the Z cancels each other in some sense. And then, not cancels, only the real part stays, is left. And then you need to figure out what is the correct condition on the coefficients. There is such a condition. And it is very interesting for people dealing in Fourier analysis and things like that. Also like all the group representation theory has to do with such things. Okay. Completely positive map. So, I mean, the following lemma is so stupid and so important that I love it. I mean, I don't know, I think it's okay, lemma. For every X in your life, I don't know, in an operator system, X is less than 1 if and only if this matrix is positive. In M2 of S. Why do I love this lemma? The proof is one line, we just check it. Let's check it. So proof, right, you can put S in some B of H. S is in A, which is in some B of H. And for every X in eta in H, well, just compute this thing. I don't like X, let me call it A, okay. Because I have a psi, it's too much. Well, what's the computation? It's supposed to be something like psi plus psi A eta plus A eta psi plus eta, which is greater than or equal to psi norm minus 2A eta psi plus eta square, which is, well, so this will be greater than 0 if A is no less than 1. So this is one direction. And if A is no greater than 1, then it's not hard to choose psi eta such that psi A eta will be less than -1. And then this red thing will be negative. Okay. So, but what does this lemma tells us? It tells us that if you know that your map is too positive, then it is contractive. If it is too n positive, then it is n contractive. So if it is UCP or CP, completely positive, then it is completely contractive. Do you see it? Again, we know from before, from the previous discussion, if I go to page 4, in page 4, we showed, and it was easy for us, although we used this tricky thing we knew about the GNS, that if you are a unital contraction, then you are positive. In general, the converse is not true. There are positive maps that are not contractions. The worst thing that can happen is that they can get norm 2, right? But if they are UCC, unital completely contractions, then they are unital completely positive because of this theorem. Now he claimed that the converse is true just because of this lemma. Because if you are too positive, then you are contractive somehow. So if you are 2n positive, then you are n contractive. So if you are completely positive, you are completely contractive. The 2n level implies on the nth level, which I think is very cool. Before moving on, before writing this, let me just give you a strengthening of like a small exercise that that is just a strengthening of the lemma. Show that for every AB in S, A star A is less than or equal in B. This inequality is, of course, written in A. If and only if this matrix is positive. 1A, A star, B. Do you see why this is a strengthening of a generalization of the previous lemma? So the previous lemma was this lemma only with B is equal to 1. To say that A star A is less than 1 is equivalent to say that the norm of A is less than 1, right? Okay. So, claim phi from S to T unital to positive imply contractive. Proof immediate from the lemma, right? Claim, another claim that is very useful and sometimes called the Schwarz inequality or Cauchy-Schwarz or Cadison-Schwarz, but let me call it Schwarz inequality. Let me write it. I mean, okay. Let phi from S to T be unital to positive. Then phi of A star phi of A is less than phi of A star A for every A in S. Again, the multiplications here are done in C star algebras. Okay, so S sits inside A and T sits inside B, and the products are done in B and A. Okay.
Why you mean assuming that A star A is in S?
No, I mean the product. Okay. Sorry, you're right. Yes, I can. Okay. No, let me write it like this. Okay. Let me. It doesn't matter. Let me write it like this. It's better. let AD be unital sister algebras. Okay. Yes, and okay. So proof. So here I'm going to use the exercise. Yes. So we know that 1A00 star 1A00 is greater than 0. This is 1A A star A, which is greater than 0. So by 2 positivity, or phi2 is positive, means that phi2 is positive. But this is nothing but 1 phi of A star phi of A star A. By the exercise, it means that phi of A star phi of A is less than phi of A star A. Another claim, maybe I should have done this claim before the last one. Let phi from S to T be completely positive, then phi is completely bounded with phi is equal to phi completely bounded, which is equal to phi of 1. In particular, UCP implies UCC. And we already know that UCC implies, that UCC implies UCP. So this answers once and for all what are the correct maps in our category. The correct maps in our categories are originally we said they should be UCP plus UCC, but now we can assume that they are just UCPs or just UCCs. It doesn't matter. Automatically we have the other one. Okay, so you can imagine that it's, in some sense, it is, well, in some directions, if you want to assume something, you assume the stronger, I mean, somehow being UCPs, well, it is equivalent to being UCC, but in some sense it is stronger. So if you want to use the strong property of UCP and UCC, usually you assume that your map is UCP. If you want to prove that the map is UCP, usually it's easier to prove that it is UCC somehow. But okay, never mind. I mean, this is not, we can think about it. I mean, they are equivalent. Anyway, proof of the claim. We more or less have everything in our end. So obviously,
Right?
yes.
So this leaves, like, there are completely bounded maps which are not completely positive, like without assuming unital, or not? I mean, when we proved unital contractions are positive, right? I guess there are examples of contractions which are.
Yes, no, okay. Yes, and yes. So yes, but it is not that far from that. So in fact, unit or completely bounded maps are going to be maps that are similar to unit or completely contraction maps. What do I mean by similar? I mean that
Again, what was the sentence? I think I didn't hear you.
in fact, UCBs, unit or completely bounded maps,
כן, סליחה.
are going to, no, not slicha, it's very important, it's highly known. They're going to be just taking a UCC or UCP, this is the same thing, and multiply it by an operator from the right and its inverse from the left. So take a simple. So this is an example of UCB, and then Vern Paulson showed it is the only example in the world. In fact, this was his way of solving an open problem, or maybe I will give you a brief. I will tell you briefly the story because I don't know if I want to go in this direction. There are many things that I do want to do, and we're in the middle of the course. But yes, that's a very interesting story there. Okay, so but right now let's prove this. So obviously we have all of these. Let A be Aj, Aij in Mn of S with, okay, maybe let me use capital A, with no less than 1. Right, so I just need to show that this is less than that. Okay, so because it's contraction, we know this from the lemma. Because of 2n positivity, we know that phi 2n of this will be positive, namely that phi n of in, phi n of a, phi n of a, phi n of in is greater than 0. So from the, well, yeah, yes, you need to do another step to say that to take out a scalar. I will skip this, but you can take out this to take the norm of phi n I n out, divide it, and then use the lemma. But essentially, it's from the lemma. We have this, but this is nothing but phi of 1. So this shows that the completely bounded norm of phi is less than phi of 1. Okay, so this should not be surprising. Claim, also we more or less we know it. I just want to I don't know, to verify that we know everything. Let f be linear functional, then
Guy?
yes.
Just to make sure, you are missing stars on the lower left A's, or it's intentional without a star in the previous proof?
No, I was wrong. Of course, I need stars. So star and the star here, and the star here. And that's it, I think. Thank you. Okay, so let f be a linear functional, then it is completely bounded, and its completely bounded norm is the norm of f. If f is positive, if f happens to be positive, then f is completely positive. Now, if we knew that phi of 1 is equal to 1, then, well, okay. I mean, there is something to prove here. Okay, we still need to prove it. We don't have here anything for free, but once we know the first part, the second part is for free. Do you agree? I mean, once I know that phi is completely bounded and the norm of f is the norm is the completely bounded norm of f, then of course that if f is also positive, then it is completely positive, because well, you can divide it by f of 1, and then it will be unital contraction, and therefore it will be positive. But the same is true for any level, so because of the first part. So it will be UCP, but then after you multiply by f of 1, then okay, so okay, I will write this. So let me write the proof and move to page 8. So proof. So let Aj be an n by n matrix over S, and I want to show that Fn of Aij, I want to show that its norm is less than the norm of F times the norm of Aij, right? This will tell me that that the completely bounded norm of F is less than the norm of F, which is when therefore is equal. So I can rephrase it like this: need to show that for any psi and eta unit vectors in H, such that S is in V of H, eta times Fn of Aij psi is less than or equal to F times Aij. This is equivalent. So let psi and eta be such vectors. Let psi be alpha 1 times alpha n, eta be beta 1 until beta n, in C to the n be unit vectors. Okay, it just an easy computation. Maybe it's better to leave it as an exercise, but I will do it anyway. Then eta Fn of Aij of psi. When you do the computation, you get F Aij beta I bar alpha j, which is F of beta I bar Aij alpha j, which is less than or equal to the norm of F times the norm of beta I Aij alpha j, which is equal to, yeah, so I'm going to do the following thing. I'm going to write the norm of F times the norm of the 1-1 entry of the matrix So I want to construct a matrix, I don't know, capital Xi, that will be alpha 1 until alpha n, and then just zeros. And capital eta, that will be same thing with beta. And here I will have eta star aij psi. So it is, of course, less than or equal to the norm of f.
Guy,
Yes.
I'm sorry, I think I'm a bit lost, but in your second need to show Xi and eta are unit vectors in H, how does it compile with Fn acting on them? Aren't they in H to the n?
In H to the n, thank you. No, sorry, Xi and eta not in H, in C to the n. So, sorry, thank you for that. Sorry, it was my confusion. Okay, so I would go over the details. Let me just finish here the last line, and I'll go over the details. This is less than f times aij. Okay, now I'm good to go over the details. Okay, so you're right. What I did was like this. Recall that f, I go to the previous page for a second. Recall that f is just a linear function. So it goes from S to C. So Fn maps Mn of S to Mn of C, right? So to show that, I want to show this inequality. To show this inequality, it is enough to fix two unit vectors in the Hilbert space in the range, which is now C to the n, because I think of Mn of C as B of C to the n, right? And apply this matrix on them, and to show that this is less than what I want to have. So this is equivalent. And I'm just doing a computation. Now, it really doesn't worth to go over every quality here, but you can do it yourself. But you do the computation, and at the end, I'm left you with something here that I just want to convince you that is less than the norm of Aij, of the matrix Aij. Now, I'm not saying that what I'm doing is the most efficient way to do it. Maybe, I'm guessing it's not. Maybe you can give a better line. But from this point, deduce that the norm of this is less than the norm of the matrix Aij. What's the way I chose to do? But maybe it's not the most efficient way. I chose to view this sum as a 1-1 entry of a product of three matrices. Now you should figure out which matrices, but it's not hard. One of them is the matrix that I'm interested in its norm. One matrix is this, and one matrix is that. Sorry, can you wait a second? Okay. So, since these guys were unit vectors, then the norm of the matrices is less than 1. So you can remove them, and you're done with what you want. So okay, this is a computation. I mean, there's nothing really interesting going on. Okay, so we show that the completely bounded norm of f is equal to the norm of f. Now we're done. Why? Because we know that now 1 over f of 1 of f, once that you know the previous argument, then this is UCC, right? But we know that UCC are UCPs. So F is CP. Okay? Okay. So I'm just collecting now many things that we need to know, and we're trying to establish our category, to understand it, to understand the morphisms. So this is what we're doing. Okay, so let me move on. If you have any questions, you can interrupt me at any time. Here is a quick exercise. So, well, it's a very easy exercise. You don't need to do it. You just need to believe it. I can always consider matrix valued functions over a compact Hausdorff space. Okay, so if I have a compact Hausdorff space X, I can plug, I can consider I can consider, I don't know, Banach spaces evaluation of it or whatever, but I think about functions from X to Mn. But this thing with pointwise multiplication. So when I do pointwise multiplication, I mean you use the product of Mn. Okay, so with pointwise multiplication, with pointwise star multiplication, and norm, which is what you think it should be, supremum over all x's in X of Fn of f of X. Here you take the norm of Mn, is a sister algebra, and it is isomorphic. Well, it has to be isomorphic, in fact, to Mn of C of X. Why do I say that it has to be isomorphic? Because once you have this isomorphism, then, well, it respects everything, so somehow it is immediate. Yes, and of course, elements are positives if and only if fx is positive for every x. Okay. So theorem. Why do I call this a theorem and not a claim? I don't know. Let S be operator system, T a function system, phi from S to T be bounded linear map. Then, I mean, no assumptions on phi. Well, we always assume, right, that they are bounded linear, but no assumptions on phi rather than that. Then phi is completely bounded, just because the range is commutative. Phi is completely bounded, and its completely bounded norm is the norm of phi. And if phi is positive, then phi is completely positive. And I claim that this is immediate. Why? Because we just need to think about the evaluations, and the evaluations are going to be linear functionals. And we proved it for linear functionals. So we are more or less done. This is what I claim. So proof. Without the laws of generality, we can assume that T is C of X, as always. And for every X in X, the evaluation of X, composition with phi, is just linear functionals, a linear functional. What did we prove about linear functionals? Well, we proved this for linear functionals, right? So by previous, what was it? A claim, lemma? I don't know. Claim, lemma? How did I call it? Claim. By previous claim, the supremum. Okay, so before, without taking a supremum, I mean by previous claim, you know, let me write this in another column. You know that the evaluation at X of phi, norm n, is equal to the norm of the evaluation of X of phi, right? This is by the previous claim. But now I'm going to insert here supremum X in X, supremum X in X. This is equal just to the norm of phi n, and this is equal just to the norm of phi. Cool, right? Similarly, phi n is greater than 0 if and only if its evaluation is greater than 0 for all x, if and only if well, evaluation in x of phi itself is greater than 0 for every x, if and only if phi is greater than 0. So because you do it pointwise, I mean, you do it at any point separately. So once you proved it for linear functionals, you proved it. Okay. So I'm done. I'm done with this theorem. Remark. We showed that when the range is a function system, bounded is equivalent to being completely bounded, contractive is equivalent to being completely contractive, positive is equivalent to being completely positive. So no surprising in this area if the range is commutative. What about the domain? So same thing goes over the domain. It is a bit more difficult, but let's do it. I mean, this will be the last thing we're going to do today, but let's do it. So what I want to show now is that, okay, maybe before that, let me write a quick exercise. If A is a positive element in a sister algebra, alpha ij is a matrix of scalars, then, which is greater than 0, then alpha ij A is greater than 0 as a matrix in Mn of A. Now, this is an easy exercise. Just apply it on vectors or something like this, right? So if you take a positive element and a positive matrix, and you consider this matrix that is I don't know how to call it, but you take a positive scalar matrix and you plug in some positive element in all of the entries, then it is still positive. I'm just going to use it, so I wanted to call it an exercise, but it's an observation if you want. So theorem, this is originally due to Steinspring, which we'll meet also next time, I think. If phi goes from C of x to t, T operator system is positive, then it is CP. It is completely positive. Now you should tell me, Guy, wait a second. Why do you assume that the domain is all of C of x? Is this true also only for just function systems? Is it true also for function systems? Let me tell you the answer. You know the answer of that. We gave an example.
Ken, Arvidson's example.
Arvidson's example, right? We took a commutative function, like a function system that lived inside continuous functions on the circle. It was positive, but not completely positive, but not too positive even. Okay, so maybe a remark before I prove the theorem. It is not true. It is not true for function systems that are not C-star algebras in the domain. See Arvidson's examples. Arvidson's examples that we showed today. Okay, so let's prove it. So do you all know what is a partition of unity? Is there anybody here who doesn't know what a partition of unity is? So if maybe I'll remind, but I'm not going to give all the details because it is I don't know, kind of basic. Okay, so I will remind it when we get there. Let f be positive in Mn of C of x, which is the same thing as C of x Mn, i.e. for every x in x, fx is positive matrix, need to show that phi n of f is positive. Let epsilon be greater than 0. Find a partition of unity, חלוקת יחידה בעברית, UL. So by this I mean that UL is a continuous function, that the sum of the ULs are 1, finite menu, okay? Just a finite partition of unity. And that each UL sits between 0 and 1, such that and XL, maybe not in parentheses, and XL in UL, such that f of x minus UL of x, f of xl, L goes from 1 to n, is less than epsilon. So when I take the supremum over all x is in x. So the idea is that we can approximate our function f by פונקציית מדרגות כזאת. Okay? And you can do it using this partition of unity. Okay? Now, what are these guys? These are scalars. I mean, partition of unity, I took it to be not matrix value, but scalar value. This is just complex numbers. This C. This is a fixed, for every L, I have an n by n matrix. So now I write the following thing. But phi n of UL of X times f of XL is nothing but phi n of, so ULX is a number, and this is just a matrix, AIJL, I don't know, let me call, let us call FXL, this matrix, AIJL. So it's greater than or equal to 0. So this is equal to phi of, to the matrix whose entries are UL of X and AIJL, which is, since phi is linear, this is just a scalar. This is AIJL phi of UL. Yeah, so sorry, no, I phi x on C of X. Sorry, here I needed to do it. See, sorry, this UL of X, well, it is in C, but for any X it is in C, so it is a function. So here I meant this works on function. So this is UL times this, UL times this, UL times this matrix. Yes. UL. But this is positive. This matrix is positive. Positive matrix. Positive matrix. Positive matrix in M and C. And this is positive element in T. So by the exercise, this is positive. Thus, we approximated, right? This thing tells us that we approximated F as the sum of n positive elements. So thus, F, phi n of F, is epsilon closed to the sum of n positive, it's not the same n. So this is a m. It's because of the time. I needed to finish before. So that's m positive elements. So sum of m positive elements is also positive. And if you have epsilon close to something positive, positive elements is something that is closed. So it means that phi of n of F is positive. So phi n of F is positive. Now we are done. Okay, I know we're out of time. Maybe I'll just quickly go over the details again, and we're done for today. Okay, So we wanted to show that whenever we have a function from a commutative sister algebra, whenever we have a linear map from a commutative sister algebra into a function system that is positive, into an operator system such that this function is positive, then it is completely positive. And the idea was like this: we need to take an element of Mn of C of x, and to show that phi n of f, right? This f is like an n by n matrix of functions, or a function that is Mn valued. This is the same thing. So we need to show that phi n of f is positive. And the idea was to do the following thing. I can approximate f by a linear combination of fixed matrices, fixed complex matrices, times scalar functions. This is by this partition of unity trick. Now, so I have here fixed matrices, and here I have positive functions. So when you apply phi n to each of these guys, it will be positive. How come? Because of the exercises I mentioned here. This is a positive matrix. This is a positive element. I mean, phi n of this is a positive element. Therefore, phi n of this time, this matrix will be positive, will still be positive. So this is what I explained here. Maybe in too many words, but here I explained, there is a delay, yes. Here I explained that when you do it on each of the summand, you get something that is positive. So eventually what you did, you showed that phi n of f is approximated by the sum of m positive elements. The sum of m positive elements is positive, because sum of positive elements is positive. And to say that you are close to being positive means that you are positive, because the positive elements are closed. So this was the trick, and then that's the way we're done. This is like you prove things in right, like you prove things in I don't know, measure theory. Sometimes you prove it for function madrigot, for BAM functions, and then you do something that tells you that, okay, you are not far from it, then it is true. That's the idea. Okay, great. So we will continue next time. I hope that it will be frontal again and not like this. Good. So have a great week.
תודה.
Yes.
Thank you, Guy.
שאלות משהו? אלון?
כן, שאלה קטנה, small question. Will we see that, I guess it's not obvious yet, but that any, like assume you have an operator system in BH, which is commutative. I mean, only the operator system itself. It can be realized as a function system. Like all the time when we set function system,
by function, you have operator system. What do you mean by when you say it's commutative? What's the meaning of being commutative operator system? There is no product.
Yeah, like the products in BH commute, but I guess then it's directly from Gelfand duality again.
If the sister algebra is generated inside B of H, it will be commutative system.
Yes.
Therefore, by Gelfand transform, it is continuous function.
Okay.
יופי. טוב, אז נתראה. ביי חבר'ה.
ביי.